Привет. Ау. Алик, слышишь меня? Hi, Tamoki.
Hi, Misha. Thank you for your invitation.
Great to hear it. How
Yeah. It's a time for sleep in Japan, but anyhow.
Is it like 12-hour difference, right? So it's you have like what's your local time?
It's a 10:30 in the evening.
Oh,
okay.
Yeah.
It's okay.
Yeah. Well, we are not able to keep balance between you, Europe.
It's okay. No. I'm just curious for attending this.
Sigma is a surface. Sigma is some remote surface, or just surface, two-dimensional surface, maybe smooth surface. And sigma tilde in sigma, in T star sigma, is an n-fold cover. Well, fold cover of sigma with respect to the ordinary projection, and also, which is very important, it's just that sigma tilde is Lagrange. So the kind of principle which I'm trying to explain is the following: just family of such sigma, family of such sigma tilde, up to, well, family, that means that I consider just family, well, just family up to Hamiltonian isotopy. And out of that, you can produce two objects. Actually, one object is just some cluster variety. Over complex numbers. And on the other hand, you can also produce, another way, you can produce cluster variety over well, tropical ring. So RT or maybe QT. Maybe QT is more adequate in this situation. And the relation between the two objects is given by the WKB, and kind of this arrow, well, arrow means that it's not very formalized object, but nevertheless, it's here, it's just kind of quantization. Or other way around, that you have a map in reverse direction, h goes to 0. And here, well, this map is, well, kind of, well, this is more or less the procedure of Gayota-Murnitsky, GMN, which, well, and I'll try to, well, I'll try to explain this picture, and I'll consider mainly the toy model for that. So my toy model will be the following. The sigma is just complex numbers. So this is this surface sigma is not necessarily complex. It could be just real, but and what was I was speaking about the higher complex structures is just this case where you need to consider sigma real. But in my case, it will be just complex, and then the family of so I will consider the following the family of Lagrangian submanifolds, so family of sigma. Tilde will be, in my example, will be the versal deformation of a singularity, of the singularity E8 in my particular case, just for example, just to show that even with the E8 you can do something, compute something by hands. So what does it mean now? My example, the versal, well, this E8 singularity is a curve. Well, it's planar curve with singularity E8. So it means that you have your function f, which depends on xy, which is equal to x to the fifth plus y squared, and plus versal deformation. So you have something like a1 x cubed plus a2 x squared plus a3 x plus a4 plus a5.
It should be x to the fifth plus y cubed. Y cubed.
Sorry?
X to the fifth plus y cubed.
Oh, y cubed. Thank you. Thank you, of course. Thank you. Yeah, plus a6x2 plus a7x plus a8, and all that times y. Well, it doesn't really matter what I'm going to speak, but just to make precise the statement. So I'll just f will depend on this a's parameter. So I have a family of curves. So this my curve sigma tilde, which will depend on parameter a. It will be just the space of solution xy such that f a of xy equals 0. Now, what I want to do, I want to construct out of that. I will construct a cluster variety of type E8. Well, cluster variety of type E8, fine type, well, the construction goes as follows. So here it's just will be my first leg. So I take the family of curves and then construct cluster variety. So, for a moment, I'll use the knowledge that cluster variety of type E8 is just, birationally isomorphic to the space of configurations, space of configurations of 8 points, 8 tuples of points in P2 in two-dimensional projective plane. So, I'll also explain what is the relation between that, but a little bit later. But why it's the case? But for the moment, I just believe me, and for those who do not know, and I'll try to construct this. Well, I want to say the following: that for every curve sigma tilde in my family, I'll construct a point in this cluster variety. So I construct from the curve sigma tilde a, I'll construct a tuples of points. And the idea is more or less the following. So the construction is the following. So I take the, I replace my function fa. So let's big F a bar will be the f of x, fa of x, h d over dx, where h is some parameter. So I construct, well, maybe should put here h as parameter, but it's not really so important. So, well, I'll omit this h here. So it will be a differential operator. So, well, FAH will be something like h cubed d over dx cubed plus x to the 5 plus a1 x cubed plus plenty of term plus a8 h d over dy. So I have some differential operator, and now I construct a vector space V, which will be the kernel of this operator. So it means that it's just the space of all function psi, such that FAH psi equals 0. Now I claim that, well, and of course, as this vector space is just a differential operator of the third order, so it means that it's just three-dimensional. So dimension of obviously dimension of V is equal to 3. So it's just three-dimensional vector space. But in this vector space, there are some distinguished vectors, distinguished one-dimensional subspaces in V. Namely, so if f psi, FAH psi is equal to 0, then according to WKB, psi is proportional to, well, asymptotic when h goes to 0 to the exponential of the 1 over h, the integral of y dx, where just y is a solution, y is a solution of f, now little f bar of xy equals 0. So we have a curve. This is, well, we have a curve, a cotangent bundle to C. So we have cotangent bundle to C. To our curve sigma is just cotangent bundle to C, which is just my space of xy. There I have a curve, and this curve, on this curve I can restrict the canonical one form and take the integral of this form. Well, since the curve is a Lagrangian, just for dimensional reason, this is, well, this function is locally canonically defined, but only locally, of course. So we have a solution of this equation, and well, it gives you a well, locally outside of singularities of the projection of our curve, we have actually 3 different asymptotics of outside. So we have well, now let's consider the situation then for x large. For x large, y is equal to x to the power 5/3, 5 over 3. So now our function psi is proportional to exponential of, well, some coefficients times 1 of each times x integral of x to the 5 over 3 dx, which is equal to x of 1 over h integral of x to the 8th a to the 3 dx. No, sorry, just x to the 8 to the 3. Well, once again, x to the 8 over 3 is a function which takes 3 different values, and let's denote x 8 over 3 is just 3 numbers, which I will denote by z1, z2, and z3, and I arrange them in of x. So it's 3 functions of x. And I require that real part of z1 be less, they're arranged according to their real parts. Real parts of z2 according to real parts of z3. And therefore, we have if you fix, well, of course, this arrangement depends only on the arguments of phi, not on the of x. So the ordering depends only on arg of x. And therefore, our space V contains a subspace W1, which is the space of all psi's, which are proportional to e to the z1 over h for given of x. Maybe I should write the following thing. V contains the space W1, which is function of argument of x, of psi, such that which are with asymptotics x of z1 over h, and also the space is a dimension is equal to 1 of W1 is equal to 1, because this is a least growing exponential. So therefore, if you add any other function, well, it's well defined there. If you add some other function, it's spoiled. This is symptotic spoiled, and therefore also it contains the space W2 of argument of z, which is psi such that it's proportional, or well, I'll write like that. So asymptotics is less or equal, not faster than exponent of z2 over h, and this is a dimension of W2 is equal to 2. So therefore, you have in the space V, you have arc of x. If you for given arc of x, you have a flag, two-dimensional flag. Complete flag in the space V. V is three-dimensional, so it's one-dimensional. It's two-dimensional. You have a complete flag, and this flag changes. Well, if you move a little bit the argument of x, of course the flag doesn't change, but it changes if under the condition then if one of these two inequalities become equalities, then the flag change. So when it happened, so if x is real, then you have the following picture. So we have, this is Z3, Z1 and Z2. Well, Z1 and Z2, it's not clear who is the first, who is the second, because they have the same real part. And the then well, it's X real. If X is not real, this picture rotates. So for X not real, the picture rotates, and every time, now I'll plot on this X plane. So on this line corresponds to the situation. Then, well, here the W1 changes. So if you go, X becomes a little bit, well, real positive. If you add a little negative imaginary part, so Z2 becomes larger than Z1. And if you add a little bit positive imaginary part, then Z2 is less. So the only thing which changes, it's W1, and W2 doesn't change. So it's W1 changes. So you have the following picture. You have 8 axes where W1 changes. So these are W1 changes. I would just indicate one. And they have, for example, 8 axes. Between them, where W2 changes. So we have a family, therefore, in W2, so you have 16 flags in V, which is 3-dimensional, and one can draw these flags in projective, well, in the projective space. We have the following picture. You have, so what's flag? Is it just a point on the line? Maybe I should, sorry. In the, just I'll draw a picture in P of V, in the projectivized version. So you have you have 8 points and 8 lines. And therefore, this picture gives you just 16 flags. So, well, for example, there is one flag which is line and point, and you move a point, you get the same point, same line, but another point. Then you move line, you rotate line, etc. So we have 8. This picture depicts exactly these 16 flags in such a situation. Then you sequence of flags such that each time you alternatively change the first and the second, one and 2-dimensional subspaces. So, of course, the space of such configuration is the same thing as 8 tuple of points. In P2. Now, it seems to me most of the audience know that A-tuple, the variety, cluster variety E8 is just 8 tuple of points of P2, but I'll explain another way how another way to obtain another way to obtain 8 points out of E8. Now I have no singularity, just Dinkin-diagram. So I obtained from singularity. Now I want to obtain from Dinkin-diagram. well, the procedure will be the following. So I'll just go to something which I prepared before. So we will, once again, it's just I do for E8, not because it's just my favorite. Well, you can exercise, home exercise, do it for other your favorites singularities. It can be done for anyone. So let's consider the following situation. Let's consider the Dynkin diagram for E8. So this is it's drawn in black. Now let's do the following procedure. So you have 3 valent vertices you surrounded by hexagon, and all other vertices you surround by squares. So you have a graph. Now you make it bipartite. So this graph, you can color it in, well, I will call these little things black, but white, sorry. It's just because usually that you draw it on a paper, then you draw a little circle and the circle is white inside. But here, well, these big things are white, are called white vertices, and little things are black vertices. So you have these vertices you color in black and white. And also, if you have a corner, a black corner, then you add some white vertices on it. So here you have, add one here, one here, one here. So it's just a standard procedure. So you have this picture, and I claim that this picture has to do something with a tuple of points in P2. Now, what's the picture here is just a tuple of points of P2, namely the 8 points which I consider is just the points 1, 2, 1, 2, 7, 8, XY, 7, 8, and 9, 10. So you have 8 points, and it's clear that looking at this picture of on these points, all other points which I didn't mention in this list. So it's well, 8 tuple. If you look at this 8 tuple of points, then you can restore the points. Well, the points. Sorry, points A, B, C. 3, 4, 5, 6, 7 can be restored, well, are determined by this 8. So just, well, it's clear from this picture that, for example, point number number 3 and 6 is just intersection of a line xy with the line the line 8, 7 and 1, 2, etc. So point A is intersection of a line 9, 10 and 1, 2, and well, all others can be restored.
Question 7, which in both sets.
Sorry?
7 is in both sets, so it's clear that it can be restored from 1.
I just didn't understand your first beginning of the sentence.
Point 7 is in both sets.
Yeah. Point 7 is, yeah, sorry. 7 is here, I should erase it. Of course, it's just in the first. So this is well, you can restore from some another. And on the other hand, now what you have at the end, you have, let's consider the configuration of points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, ABC. So it's a configuration of points which, well, we are not now there's a certain relation between them. So it means that some points, some triples of points belong to lines, for example, 9, 10, and A on the line. And this diagram encodes this position. So we have a collection of points satisfying certain relation between them. So some of them belong to a line, some triples belong to a line. And each time you have a black vertex here. The corresponding 3 points belong to one line. For example, A, B, and 1 belong to one line. A, B, and 1 belong to one line. B, 1, and 5 also belong to one line. B, 1, and 5 belong to one line, etc. So just you can draw this picture out of that picture, looking at this configuration. So, for example, you have sorry, I did something wrong. Sorry. Here is C. Here is 9, and here is 10. It's just my. It's not 0.11. It's 9. So you just draw 3 lines, ABC, for example, and then it's clear that the point 1 belongs to the line AB. So you draw the line AB, and you put the point 1. Then the point 5 is also on the same line because it belongs to the line B1 and 5 on the same line. So 5 also on the same line, etc. So just looking at this picture, you can draw this one, and vice versa, in principle. So therefore, from this bipartite, from the Denke diagram, you construct bipartite graph. From bipartite graph, you construct your configuration of points on the plane. This correspondence is also very useful for the following reason, that you have, well...
Volodya, may I ask you, so we should look at different 8 tuples of points on P2. You seems to be constructing one each.
No. You just take any 8 tuples of points.
Yeah.
Well, in general position, of course, because you want all these lines to intersect. Well, do not coincide, for example. And for any,
this diagram is kind of encoding some kind of matroid of this configuration.
Yeah, of course. It's just a matroid. It's just a matroid. Of course, this diagram encodes a matroid. But what's nice also about that is this diagram it's not only just encodes a matroid, but it's also looking at this diagram, one can construct coordinates on the space. So given just not a matroid, not just configuration of points, but just concrete realization of this configuration. So if you have a realization of this configuration of 8 tuples of points, so one particular 8 tuple of point, will map to to C8. In my case, where I draw over reals, so it will be actually to R8, but it doesn't matter. So RC star 8 and C R star also. So there is looking at this picture, I can just construct parameterization of this space, and the parameterization goes as follows. So these vertices, white vertices correspond to one-dimensional, the points on projective space, or the same thing, so one-dimensional subspaces in I will speak about R, but it doesn't matter, in R3. So let's choose a basic vector in such a vector in each such subspace. So therefore, for any, now we just for any, what I'm going to do now is just I want to construct starting from this picture, I want to construct 8 numbers. Starting from the configuration of 8 points, I want to construct 8 numbers.
Sorry, what are points X and Y?
Pardon?
What are points X and Y in the quiver? Like, where do they come from?
Well, in this quiver, they just, well, I just want to say that there is here, well, this picture corresponds to configuration triangle and 2 points on one side, 3 points on another side, 5 points on another side. But I want to say that such configurations are in bidirectional correspondence with the configurations where I have just 8 points without restriction.
Okay.
So there are two configuration spaces which formally are described by 2 different conditions. In one case, you have 13 points with relations. In other points, you have 8 without relations. But these 2 sets are in bidirectional correspondence because you can construct one configuration uniquely in terms of another. So XY you don't see on this picture. I hope that, yeah, you should get. So choose a basic vector on in such subspace. Well, sorry. We choose a basic vector, and then every time you have a vertex and you have a black vertex to each such subspace. So, and suppose you have a black vertex. You have V1 and V2 and V3, 3 vectors, which are sitting inside. So we can construct, of course, V1 plus V2. Well, we have a choose a relation for every black vertex. So the relations means that you choose coefficients A3, A1, A2, such that V1, A1 plus V2, A2 plus V3, A3 is equal to 0. And of course, choose a basic vector, so non-zero vector, choose a non-zero relation, non-trivial. And therefore, out of that, I construct, so therefore, well, coefficients of these relations don't give numbers on edges. So we have numbers on edges of the graph. And out of that, you can construct numbers. Out of that, you construct numbers of faces, numbers on faces. On faces of the graph, well, gamma of gamma. Indeed, if you have a face, well, for example, a square, but it's the same thing as, so you have A1, A2, A3, and A4 on the edges. So for that, you associate the product, well, A2, A4 over A1, A3, the, well, kind of monodromy. So you consider these A's as maps between 2 one-dimensional vector spaces, and the product of them is just alternative product, is the monodromy around this face. And the claim is that, well, these numbers, well, A3. So these are coordinates, well, cluster coordinates on the space of configuration, the configuration space.
Well, if you have face hexagon, no, not square, then do you have any interpretation for gauge group? This face coordinates are invariants of gauge group action, right? So
right.
So what?
But even for 6, well, gauge group is a abelian gauge group. It's not really a very important gauge group here. It's kind of abelianization. So, well, here there is no difference between hexagon, for example, and well, if you make mutations, then there are some problems, of course, if you have hexagons. But interpretation of coordinates is not nothing special. So this is a, if you have something like that, so you take product of even divided product of odds.
Okay, yeah.
It doesn't really matter. The claim is why we take this ratio, because if you take just coefficients, these coefficients, they are, what I did, I just have chosen vectors and I have chosen relations. Every choice is up to a constant. So I can change this.
Yeah, right, okay.
I make another choice, then the numbers A's change, but this expression do not change.
Mm-hmm. Yeah.
So therefore, there's coordinates, and these are the so the now, well, the question is now. So I have I've made have an example. Then we have a family of, well, I return to the, sorry, this is where it is kind of lost. Yeah. I had a family of the curves. Out of this family of the curves, I constructed, actually, well, I just parameterized it by cluster variety. Of course, this 8 points is just an example of that. And on the other hand, yeah, and the question is, in which sense this is, well, now the second leg, how I obtain from pass from this space to this one. Well, in one sense, if you have a cluster variety over C, of course you can consider cluster variety over tropical rings. You just consider the coordinates which are tropical, and you get some particular cluster variety. So this is a kind of trivial things, but the question is if one can do something more straightforward. So having a family of surfaces, I want to construct a point in a tropical space. And for that, I need really to, well, my aim is to construct out of E8, for example, I want to do the following. I want to take my family of surfaces and just construct this picture out of that. So this picture comes from nothing for so far. It's just from fact, from my knowledge that well, about the diagrams.
Je sais de la France et qui ne changera pas. En période normale ou en confinement, si t'as pas d'oseille, tu peux me croire, on s'en fout de ta gueule.
Pardon? The question is how to pass from the next question. How to go from family of surfaces, so family of surfaces, and the graphs. And well, here I just, well, I will be a little bit more vague than before, but nevertheless, I claim something. So I want to construct a graph out of the surface, and the idea is the following. So you take, well, now I want to consider not all possible surfaces, but let sigma tilde be, well, for me, I mean that from sigma tilde, I want to construct a finite graph, or graph on sigma. So let sigma tilde represent a class in H1 of sigma tilde with value in rationals. So it's a rational class. Well, I recall that sigma tilde is just a subspace of T star. So therefore, T star of sigma. So therefore, there is a form. There is a canonical form y dx in my example, y dx, which is the canonical form alpha. And so if you take y dx restricted to sigma tilde, it's closed because it's Lagrangian, and therefore it represents some class. And I imagine that suppose that this class is integer, is rational. So it means that this form alpha restricted to sigma tilde, well, maybe I write it down like that, big N times alpha restricted to sigma belongs to H1 of sigma tilde and Q, Z. Sorry, I just can multiply it by some number to get an integer. And then how to construct the graph? The graph, I do the following. I take the map. So let's take sigma cross S1 and map sigma. There is a map which one can define sigma tilde to sigma cross S1. It's defined the following way. So we have a point here, then it's mapped to, well, on one sense, it's mapped to P sigma, P of X. Well, P of P is just a map from sigma tilde to sigma is just the standard projection, comma, integral up to X of alpha. Of course, this map is defined. I need to choose some basic point here. And this one, well, n alpha maybe. This belongs to R over Z. So this integral doesn't depend on the path if you consider it modulo integers. So this is well defined as an element of the circle, and well, so you have this map well defined. The claim then, of course, this map is a map with dimension of sigma tilde is 2, the dimension of sigma cross S1 is 3. So we have two-dimensional manifold map to three-dimensional, and of course the image have self-intersections. So well, let's take this map, denote this map by rho. So think of rho. The space is just as a subset of sigma tilde, and this is just the points where, well, maybe it's sigma. It's better to. It's just a set of points. So this is a space of all Z in Z bar, such that the inverse, if you take P minus 1 of Z, sorry, maybe I should say well, maybe I should say the following. So excuse me, it's a little bit. So the sync tilde of rho will be the space of, well, here. Sync tilde of rho is the space of all points, the set of all x's belonging to sigma tilde, such that there exists y, and the rho of x equals to rho of y. And think of rho without tilde will be, it's a set of belongs to sigma, and this will be well, the image, it's sig of rho is equal to it's P of sinc tilde. So therefore, you what I want, well, another definition that sinc of rho is a set of all points z in sigma on the base, such that there exist z1 and z2 belonging to p minus 1 of z, such that the integral of alpha from z1 to z2 is an integer. So you have a base, and then you have the fibers, and the point belong to our singular set if there are 2 points here, such that if you integrate over some closed path, so this area is an integer. And I claim that this is, sinc of rho is a graph, is a locally finite graph. In fact, if the surface is compact, is closed, then it's just finite. If it's not, then it may be non-compact, because if you go to infinity on the plane, for example, in the case where we considered, or the case of E8, the graph is non-compact, well, not finite, because the number of points, well, this property is accumulated to infinity, but in every finite area, it's finite. So this is well, I claim finally that this graph, well, sinc of rho contains this graph gamma, which I want to, well, it's not, it's a little bit larger than the graph we want. So well, there is a, well, it's kind of even more singular powerful fit. So this graph sinc of rho has a property, for example, for SL3, for our case, for example, for E8, we have the following. There are 2 types of singularities of this graph. This graph itself has well, sinc of rho have either the only singularities, either triple points, or 6 tuple vertices. So we have either like that, and there are finitely many, or actually there are 16 of them. There are 16 of them. 16 of that, and well, unbounded number of unbounded number of the vertices which are trivalent. Unbounded, it means that well, they accumulate into infinity, and also if you change your form alpha, then of course you choose parameters such that the alpha is integer. So this is kind of not very easy to do analytically, and well, you have, but your graph gamma is just if you take the minimal possible graph which contains this trivalent vertex, then the claim is that you get a graph which is well, once again, I have no proof, but it's experimental. experimental fact that you get a graph which is either coincides with the graph which I started with, namely the graph which is drawn here. Of course, it's just a very good chance to have exactly this graph, but in generically you get something which is well, mutational equivalent. At least the pictures which I, well, yes, well, this is the way how you can get back the graph of yeah. Well, perhaps I'll stop here. Yes, of course.
Okay. Thanks, Volodya. Any questions? We have like few minutes for questions. Okay. If
can I ask a stupid as usually a question, Volodya? This configuration of 8 points on P2, do they have some relations with possibly with Del Pezzo?
I think so, yes, but I cannot. Well, yeah, there is the whole story about this relation between this E8 and Del Pezzo, because well, I'm not competent to. There is a very nice paper about that by Daniel Rudenko, which I trying to study it, but well, maybe I'm not ready to comment, but certainly there is.
Can you give once more, say the reference?
Well, the name is Rudenko, Daniel Rudenko. You can find.
Okay.
It's related to, well, he does this relation, well, he exploited to study the volumes of tetrahedra in three-dimensional hyperbolic space and find tetrahedra, not ideal. And this is a really very beautiful paper, and in particular, they use the fact that, well, configuration space of Del Pezzo has a certain classical structure, but, well, using the construction by Lloyd the period map in his this construction which I described about the monodromy of his connection on a graph, it really looks like very close to this Loyenga period map, but also this is a subject which I cannot quite understand, cannot translate it literally, but it looks like very similar.
Yeah, Volodya, do you have some special configurations of n-tuples which are important, or do you get those n-tuples generically?
No, this is a kind of correspondence, generic correspondence in generic situations. So we have generic A-tuples of points in P2 correspond to generic collection of numbers on the faces, where you have.
You also mentioned this birational correspondence between 16 tuples and 8 tuples. So
16 tuples, it's just, once again, it's just, I consider it's just in kind of equivalence between matroids. So you have 8 tuples of points without restriction. It's the same thing at 16, as the same thing as 8 points and 8 lines. Each line containing 2 points. So this is a just the same thing. So I consider from a matroid point of view, this equivalence is a little bit strange.
Yeah, I was a little bit confused. Don't you get the cyclic order then? Or I mean, cyclic order maybe in the real situation, of course, yes.
Well, cyclic order, yeah, cyclic order is just important here. In the real situation, exactly, you have, you may ask, for example, for all your cluster coordinates to be positive, and this positivity implies a certain restriction on position of real points. This is a well, there are some configuration of real points on RP2 are called positive, and sometimes are not. In this particular case, the positivity amounts just to be that you can draw a convex curve passing from all these 8 points. But yeah, there is such an issue, but well, I didn't mention it. Just if you can work it just for complex points.
Okay, thank you.
Okay, thank you, Volodya. So, yeah. And could you please send notes to me? I will post it somewhere. So.
Okay.
So next week we'll have Valia Avsiyenko. Yes, Valia, she's somewhere there, so I think it's he confirmed. Okay, thanks everybody. Yeah, and goodbye.